Okay, so this video will be solving a fairly interesting sum, and that is the infinite sum from n equals k to infinity of n choose k times 1 half to the power of n. And so to write out the first couple of terms, that looks like k choose k times 1 half to the k plus k choose 1 choose k times 1 half to the k plus 1 plus k choose 2 choose k times 1 half to the k plus 2 and so on. So I have not pointed out what k is, so k can be any positive integer. And you want to solve this as some function of k so that you can just plug in a value of k and get out what the answer should be. So the first thing you might notice with this one is that it's the sum of some binomial coefficients times something. So we can try and look at a couple of hints of some other things where we're summing up binomial coefficients to try and see what we may be able to use to solve this. So the first thing is that we are summing over n's, which is the top number, instead of the k's. But if we were to sum over k's, then we can do something quite nice. So if instead of this sum, we look at the sum k equals 0 to n of n choose k times 1 half the power of k. So I replace the n with k here, and then instead of summing from k equals 0, from n equals k to infinity, we're summing from k equals 0 to n. And so this is, right, the first couple of terms, that's like n choose 0, and instead of 1 half, let's just put in x. So we have x to the 0 plus n choose 1 is x to the 1 plus n choose 2, x squared, and so on, up to n choose n times x to the n. And so this series is the exact same thing as x plus 1 to the power of n. So this is just a series expansion of x plus 1 to the power of n. And what we have here is what's called a generating function. So what that means is that we have some function x plus 1 to the power of n, where if you expand it as a power series, which is just a polynomial or infinite polynomial in x, then the coefficients are going to be some numbers that you care about. In this case, the coefficients are n choose k, which is what we care about. So here, this thing over here is exactly the same as what's up here, except the x is replaced by a half. So here we can just replace the x by a half in this series, but that's the same thing as replacing the x with a half here, which means that this is equal to 3 halves to the power of n. Just get rid of the x. So yeah, that's the first thing that we can do. So one thing that might help us in this series is looking at some sort of power series which will have these coefficients. And the other thing is, again, we're summing over n instead of summing over k. And the other place where you might have seen that is what is called the hockey stick identity. So that looks like the sum from n equals k to m of n choose k. So the first couple terms of this will look like k choose k plus k plus 1 choose k plus k plus 2 choose k, and all the way up to n choose k. And so one way that you can solve this out pretty nicely is by looking at Pascal's triangle, which is where the name hockey stick identity comes from. So start at the first couple of things of Pascal's triangle. 3, 3, 1, 1, 4, 6, 4, 1, 5, 10, 10. And maybe let's say like we go from k equals 2 and n goes from 2 to 4. So that'll look like 2 choose 2 plus 3 choose 2 plus 4 choose 2. And we want to evaluate that. So if you look at the corresponding elements on Pascal's triangle, that'll be this guy's 2 choose 2, 3 choose 2, and 4 choose 2. And to sum those up together, what we can do is realize that this 1 is the same as the 1 over here. So we can combine these two, and that'll give us a 4. Because of how Pascal's triangle works, you can combine two elements to get an element below. So this 3 and the 1 combined to make 4, and then the 6 and the 4 combined to make 10. So what that means is we're essentially like moving down each time, and we can combine the elements. So this 4 represents this sum, this 10 represents this sum, and so the final answer is just going to be like going down and across, which looks like a hockey stick, and hence the name hockey stick identity. So for example, if we want to do one more, 1, 6, 15, 20, 15, 6, 1, and so this will be the same thing as adding on 5 choose 2. So this number over here is 5 choose 2, but then this 10 represents this sum, and so we add on another one, so the 10 and 10 combined to make 20, and 20 would be your answer. And so the final formula that you get for this is you're going down one more row, so your row represents your n value, and you're going over one more place, which represents your k. So that means that this is going to be equal to m plus 1 choose k plus 1. So for example, if you sum up to this, then that should be equal to 6 choose 3. And this is 6 choose 0, 6 choose 1, 6 choose, and 6 choose 3. So yeah, for this sum, what we found useful was generating series, and for this sum, what we found useful was Pascal's triangle. So maybe we can combine the two together to find some way to evaluate this infinite sum. So let's write out Pascal's triangle again. Okay, and so what I said earlier was that we have x plus 1 to the power of n is equal to the sum of n choose k, x to the k. And these n choose k are the values for these rows over here, where the n's are just the row numbers. So this is n equals 0, 1, 2, 3, 4. So if we multiply each of these by a corresponding x, this will be x is 0, x is 0, x is 0, x squared, x is 0, x squared cubed, 0, 1, 2, 3, 4. And what we can do is we can add up each of these rows and get that they equal x plus 1 to the power of whatever row we're on. So this is going to be equal to x plus 1 to the 0, which is just 1. This is going to be equal to x plus 1 to the 1. This is plus 1 squared. This is plus 1 cubed. This is plus 1 to the power of 4. So somehow the x to the power of k, the coefficient of that, if you fix some value of n, then that encodes what the numbers are in the rows of Pascal's triangle. But instead of looking at the rows would be like if we were summing up this way, like we have over here, where we're summing up over the k's. But over here, we're summing up over the n's. And we just saw that that looks like a sum over this diagonal. But notice for the diagonal values, the coefficients of x are the same. So for this diagonal, the coefficient, the exponent of x. So here the exponent is 2. Here, if we were to keep going, the exponent would be 3. Here, the exponent would be x. So we want to sort of group together maybe the coefficient of x squared here, the coefficient of x squared here, the coefficient of x squared here, and so on. And one way that we can do that is introduce a new variable y. And this will encode sort of what row we're working in. So we'll multiply this by y to the 0, y to the 1, y squared, y cubed, y to the 4th, and so on. And so what we have just constructed is the sum. The sum from n equals 0 to infinity of x plus 1 to the power of n times y to the power of n. And so what does this sum represent? Well, the exponent of n represents what row you're working in, and you can sort of think of this as being a coefficient of y to the power of n, so a sub n of x. And what a sub n of x is it's a function of x that encodes the row. And if you were to expand that out, that would be the sum from n equals 0 to infinity times the sum from k equals 0 to n of n choose k, x to the k, times y to the n. And notice that there's no harm in removing these parentheses over here. So we can group things together either like by considering this as being x plus 1 to the power of n, or by considering this to be some term and we're adding over these two sums. And so we notice that the coefficient of x to the k, y to the n corresponds exactly to n choose k, which is some number inside this Pascal's triangle. And so now what we have is that this infinite sum pretty much encodes every single value of Pascal's triangle in a really nice and compact way. And we also notice that if we group together these by y, so that means that we're summing over n second, then these coefficients encode each of the rows of Pascal's triangle. So what we just said was the diagonals would have a constant exponent of x. So if we were to regroup this and sum it as sum from k equals 0 to infinity, this is possible. It would be sub k of y times x to the power of k. Then this is grouping together all these terms in terms of with the x power equal, which means that we are summing over these diagonals. And so what this will look like is the sum from k equals 0 to infinity times the sum from n equals 0 to infinity of n choose k, y to the power of n, times x to the power of k. And so notice that these terms are exactly what you want here, except you plug in y equals 1/2. And so here, if k was going from 0 to infinity in this sum, then you can just pretty much switch the order of x and of k and n sum it up in the opposite order and then group things together. But because it's only going from k equals 0 to n, things may get a bit complicated. But this isn't too much of a problem because we can notice one thing, that is n choose k is going to be equal to 0 if k is larger than n. So for example, if you look at like the expression 2 choose 5, combinatorially this is like if I hand you 2 balls and I say how many ways can you choose 5 balls out of this? Well, you look at me and think I'm stupid because I'm only giving you 2 balls and ask you to pick 5. So there's no way to do that, so this should be equal to 0. But you can also look at the explicit expression, which is 2 factorial over 5 factorial times negative 3 factorial. So this is n factorial over k factorial n minus k factorial. And if you extend the factorial function to the negative numbers using the gamma function, then this denominator will go to infinity. So this would look like something 1 over infinity, which is 0. So either algebraically or combinatorially, you can argue that n choose k is equal to 0 if k is greater than n. And so what that means is that we can pretty safely extend this sum. Instead of going from k equals 0 to n, we can just go from k equals 0 to infinity. Because this over here, for example, which is x plus 1 squared, there's no harm in saying plus 0x2 plus 0x to the 4th plus 0x to the 5th and so on, because you're just adding 0. And all of that is still going to be equal to x plus 1 squared. So this sum is now equal to this, and if you switch the order of summation, then you get the same things but grouped together so that you're grouping the x things, the terms with the same exponent of x, and that'll be some coefficient b sub k of y, and this b sub k of y is exactly what we're looking for if we plug in y equals 1/2. So how do you do that? Well, now is actually pretty much the easiest step of the entire thing. Basically just notice that this is a power series in x plus 1 times y, so you can rewrite that as 1 over 1 minus plus 1 times y. So the reason for that is that you can just like distribute the exponent so that you have something to the power of n from n equals 0 to infinity. And so that's just 1 over 1 minus the common ratio, assuming that the absolute value of this is less than or equal to 1. And so now what we can do is we want to expand, well, if we expand it like so we have it in terms of a function of y, but we want to expand in terms of a function of x. So what we want to do is have this in the form of 1 over 1 minus something times x. So that way we can expand it as an infinite geometric series in terms of x. And so what we can just do is rewrite this as 1 over 1 minus y minus xy, and then divide through by 1 minus y to get that this is 1 over 1 minus y over 1 minus y over 1 minus y times x. So this is just distributing the y over and then dividing through so that you have a 1 minus something. And so now if we ignore the numerator and we say that this is like 1, then this would be the sum from k equals 0 to infinity of y over 1 minus y to the power of k times x to the k. But then because we also need to keep track of this 1 over 1 minus y, we can just throw that in at the end. So that'll be times 1 over 1 minus y, that is not a minus sign, times x to the power of k. So notice that we just got something where we have some function of y that depends on the coefficient k times your x to the k. So we have successfully regrouped these guys so that we're now summing over things with the same exponent, which means that we're summing over this diagonal. So what that means is, since these two things are equal, this sum from n equals 0 to infinity of n choose k times y to the n is equal to precisely that expression. And now what we need to do to finish off this problem is substitute y equals 1/2 into here. So this will be 1/2 over 1 minus 1/2 power of k times 1 over 1 minus 1/2. So this is just 1/2 over 1/2, so that'll cancel to be 1. And so this will just be 1 to the k times 2 because it's just 2, and that'll be 2. So I kind of cheated by choosing y to be a half over here because I knew that the answer would come out to be independent of k. But if you chose something else like 2/3, for example, then this final sum would actually depend on k. So just to reiterate what we did, we sort of were able to nicely compactify the entirety of Pascal's triangle, so all of the coefficients, in terms of this small little nice function, 1 over 1 minus x plus 1 times y. And the way that this encodes Pascal's triangle is the coefficient of x to the k times y to the power of n is n choose k, which is exactly an element in Pascal's triangle that we're looking for. And so by regrouping this in terms of y, we know that each of the row sums is x plus 1 to the power of n. And by regrouping that in terms of x, we know that this sum, through two infinite geometric series, which isn't too difficult to do, is equal to this. So yeah, that's pretty much it for this video. If you want a sort of challenge problem, this sort of trick obviously only works when k is an integer, because otherwise this infinite sum would not be equal to this, because x to the power of k would not be a part of Pascal's triangle or whatever. And so you can try and see, does this identity that n choose k times 1/2 to the power of n is still equal to 2 if k is not an integer? And so you would have to define n choose k in terms of factorials, in terms of gamma functions. And if it is true, why is it true? So yeah, that's pretty much it for this video. And yeah.